Okay, let's dive right into this explainer. We're going to strip away all that science fiction hype and look at the fascinating mathematical reality behind buzzwords you're probably hearing every single day. Stuff like deep learning, transformers, neural networks. I mean, we live in a world where your phone can recognize your face, right? It can translate languages in real time or even generate photorealistic art from just a quick text prompt. But how does that actually work under the hood? Well, today we're going to break down the actual mechanics of modern artificial intelligence. Because this is a pretty complex, multi-layered topic, we're going to follow a clear roadmap. We'll hit biological inspiration, the math engine, architectures for sight, memory, and language, the generative era, and finally wrap it up with the black box. So, Section 1, Biological Inspiration. Airplanes versus birds. To understand deep learning, we kind of have to look at its original inspiration, which is the 86 billion neurons inside the human brain. Early computer scientists saw that and wanted to build a digital version. But here is a massive reality check for you. Artificial neural networks are inspired by the brain in the exact same way airplanes are inspired by birds. Think about it. While birds flap their wings, airplanes use fixed airfoils, right? The biological brain relies on this incredibly complex chemical modulation. But artificial neural networks, they're built on perceptrons, relying purely on adjustable weights and mathematical functions. So the brain analogy is super poetic, but the actual implementation, it's literally just math. Moving on to Section 2, the math engine. Tensors, parameters, and gradients. So to make a neural network deep, we basically stack up multiple hidden layers. And the data flowing through those layers takes the form of tensors. Let's bust some jargon right here. Tensors are just multi-dimensional data structures. For example, a color image is just a three-dimensional tensor made up of height, width, and color channels. And these networks learn by adjusting parameters. You can think of parameters as literally millions or even billions of tiny internal mathematical knobs that weigh the importance of that data. But how on earth does the machine know which way to turn all those millions of knobs? Well, imagine the network is a blindfolded hiker trying to find the lowest valley in a massive mountain range. It uses a process called gradient descent. The height of the mountain represents something called a loss function, which is basically a mathematical measure of how wrong the model's guesses are. By feeling the slope of the ground beneath its feet, the algorithm takes a step in the steepest downward direction. It's trying to minimize its errors and find that absolute lowest valley. Okay, so the network knows which way is down, but how does it actually update those knobs? It does it through a brilliant 1980s invention called backpropagation. It relies on the chain rule, bringing it back to calculus class. Basically, it looks at the final error and then works backward through every single layer of the network. It figures out exactly how much each specific knob contributed to that error, and then it tweaks it. Let's break this highly complex math into a super digestible sequence. This is the full pipeline of how a deep neural network actually gets trained over many cycles or epochs. First, it initializes with completely random weights. Then, it makes a forward pass to just guess an answer. Next, it computes the loss to see just how wrong that guess was. After that, it does a backward pass, that's the backpropagation, to calculate the required adjustments. And finally, it updates its parameters. It just repeats this loop millions of times until those predictions become incredibly accurate. All right, Section 3, Architectures for Sight, How Machines See. Basic networks are great for spreadsheets, for sure, but feeding them high-resolution images? That would require billions of parameters for just one single layer. It's way too slow, and they end up just memorizing things instead of actually learning. This is where convolutional neural networks, or CNNs, come into play. CNNs drastically reduce those connections by sliding a tiny mathematical filter, called a kernel, over the pixels. Early layers might just detect simple edges. Middle layers combine those into textures, and deep layers assemble actual object parts. It's literally discovering the visual hierarchy of our world without any explicit human programming. Pretty wild, right? Now, that handles static images perfectly. But what happens when we need to process sequential data? Where the order changes the entire meaning. I mean, the cat sat on the mat, and the mat sat on the cat use the exact same words, but they paint two very different pictures. Images are spatial, but things like language, music, or stock prices, those are sequential. Which brings us to Section 4, Memory and Language, RNNs and Transformers. When dealing with sequences like translating a language or predicting the next word you're going to type, networks need memory. They have to make sense of the present based on the past.
For a long time, the go-to solution was recurrent neural networks, or RNNs, and a beefed-up version called LSTMs. Think of them like a conveyor belt with selective loading. They process sequences one word at a time, using a gated state to remember the important stuff and ditch the useless stuff. But there's a massive flaw here. Processing one word at a time is incredibly slow. Plus, they still really struggle to remember context from, say, 100 words ago.
So, processing word by word is a huge bottleneck. This led researchers to ask a really important question. Is there a way to look at everything all at once? How can a model figure out what the word "it" refers to in a really long paragraph if it has to process that paragraph strictly in order? And that perfectly sets the stage for the 2017 Transformer revolution. This completely replaced that sequential word-by-word processing with something called attention mechanisms. Basically, a transformer processes every word in a sentence simultaneously. Through self-attention, the model mathematically calculates how much it should focus on or attend to every other word in the text. This allows it to understand how totally distant words relate to each other instantly. It was an absolute game changer. In fact, this single architecture birthed modern foundation models. And it basically split into two famous branches. On one side, you've got models like GPT. That uses a decoder-only architecture, which is insanely good at generating text by just predicting the next word. On the other side, we have models like BERT. BERT uses an encoder-only architecture to deeply understand the context of the text by predicting missing words. But the key takeaway? Both are powered by that exact same underlying transformer breakthrough. Let's move to Section 5, the generative era, creating new data. For decades, machine learning was mostly discriminative, just labeling things, asking, is this a cat or a dog? But generative models, they actually learn the underlying probability distribution of the data itself. Once a model maps out the statistical rules of, say, what makes a human face actually look human, it can sample from that mathematical map to dream up entirely new text, audio, and images. Things that have literally never existed before in human history. Today's state-of-the-art relies on a couple of really brilliant architectures. First, we have GANs. GANs play this intense, competitive cat-and-mouse game. One network tries to create a fake image, and the other network acts as a detective, trying to catch the fake. They literally train each other. Then you have diffusion models. This is the tech behind systems like DALL-E and Midjourney. They work by basically reversing the laws of thermodynamics. They take pure, noisy static and denoise it step by step into stunning, photorealistic art. It's honestly astonishing to watch. Finally, Section 6, the black box, philosophy and AGI. So we've built these incredibly powerful tools that can write code or even map entirely new proteins. But because these networks have billions or sometimes trillions of interconnected, nonlinear parameters, they act as opaque black boxes. We see the data going in, and we see the surprisingly accurate results coming out. But it's incredibly difficult to mathematically explain why the model made a specific decision. And that's a massive technical hurdle when we need to explicitly trust these systems for life or death applications, like autonomous driving or complex medical diagnoses. And look, despite how magical they seem when they generate a perfect poem or a beautiful image in seconds, it's really important to remember that all current deep learning models are strictly narrow AI. They might be superhuman at their specific tasks, but they are totally clueless outside their training data. They completely lack the common sense, the physical intuition, and the reasoning required for true artificial general intelligence, or AGI, that remains purely hypothetical. This actually brings us to a famous philosophical debate known as the Chinese room argument, proposed by philosopher John Searle. Imagine a person locked in a room who doesn't speak a single word of Chinese, but they have this massive rule book for how to manipulate Chinese symbols. If someone slides a question in Chinese under the door, the person inside can just use the rule book to slide a perfectly coherent answer back out. The person outside thinks, wow, the room understands Chinese. But does it? Or is it just following rules? This really questions the very definition of cognition itself. Ultimately, the math works. The tensors, the gradient descent, the transformers, they all coalesce into something that looks undeniably like magic. But it leaves us with a profound question about the future of deep learning, and it's what I want you to take away from this explainer today. Are these models truly beginning to understand our world? Or are they merely simulating intelligence through massive, multidimensional mathematical optimization? Really think about that the next time you ask an AI to write you a story.